So today I'm going to talk about, let's see here, well, mostly talk about momentum today. We introduced the center of mass concept last class, and we'll come back to that from time to time, but for the moment, I'm just going to talk about a single particle. All right, so I want to talk about momentum. And something else which we call impulse. All right, so momentum, so if you're given a mass, say m, it's a particle with mass m, all right? We define t, the so-called linear momentum. It's a vector, all right? And it's equal to mass times the velocity. Okay, so this is the so-called linear momentum. Although I will drop the linear for the most part because we're only going to talk about linear momentum for a while, and then we'll talk about angular momentum, and then, well, then we'll have both. But for now, linear momentum, P is equal to mv. So for a single particle, you can ask, how does the momentum relate to things we've talked about already? All right, so like, why talk about momentum? Some good reasons for it, we'll see today. So let's see, I guess the thing we had before, well, we could calculate the time rate of change of momentum. Let's do that. Usually derivatives are interesting, so let's take a look at it. What would dp dt be? Well, that would be ddt of m times v, right? Now, if the mass is constant, I guess let's just talk about it. Generally speaking, this would look like what? This would be like dm dt times v plus m times dv dt, right? But for a single particle, you don't usually think about the mass of a single particle changing, right? Like dynamic mass, that's kind of weird. But I guess if this was a rocket, right? We're talking about the mass of a rocket, maybe the rocket's mass could be changing, then you could have a non-trivial dm dt. And that's interesting, but let's save that case for later, and let's just suppose that this is 0, okay? So we're talking about a single particle, a fixed mass m. In such a case, dp dt is equal to m dv dt, but hey, what's m dv dt?
Force.
Yeah, that's ma, which, as you're telling me, is the net force. Putting some words in your mouth, but yes. Right? So, there you go. We've now discovered that there's a perhaps better way to state Newton's second law. Newton's second law is even better stated as it's dp dt, where p is the momentum, it's the time rate change of the momentum. Newton's second law in terms of momentum. There you go. No. Oh, thank you. So we can integrate both sides, right? So let's integrate. Over here. So if I integrate, say from time 1 to time 2 of the net force t dt, right? What's the integral of a vector? It's the vector of the integrals, all right? This is not a line integral. This is just kind of the boring integral, comma integral calculation we did at the start of the course. Well, that will be equal to the integral from t1 to t2 if it's the net force, right, of dp dt. Dt, which, by the way, would just give me what? P of t2 minus P of t1. All right. So what I've, using the net change theorem, fundamental over calculus, if you like, what I've discovered then is that the integral of the force is equal to what? I mean, in words, this is the change in momentum. Right? Now, for reasons I don't entirely understand, some people call this J. I kind of would prefer to call it, I think it's more descriptive to just call it change in V. It's the finite change in momentum. All right? And this is in fact what's known as impulse. So this is the impulse. It's the impulse which is given to the mass m by the net force over the duration time 1 to time 2. So, yeah. So in other words, the integral of the force, in fact, gives you the change in momentum, which is what we call the impulse. Let's look at an example. So let's see here. Say this. I guess you could have a catapult, right? And then, of course, what would you put in the catapult? Well, I mean, obviously you put a cat in the catapult, right? Very good, thank you. So we're on the same page. There you go. Here's your cat. It looks more like a bat. Oh well. So you got your catapult, and then, of course, you pull it back. You know, you pull it.
Looks more like a slingshot.
Absolutely.
I'm sorry.
It's really a catapult.
I mean, it looks like what David shot Goliath in.
That'd be a sling.
Yeah. If you insist, fine.
So let's change the word.
We're getting more trebuchetish.
That is the scene.
Okay, this is before.
Why would Lincoln cut the roof?
And then after.
At this point, it might as well be Wile E. Coyote. That looks like one of his contraptions.
Actually, dynamite. Okay, so obviously the initial velocity would be 0 meters per second, right? Final velocity right after he's leaving the catapult. After he's leaving, he's left the catapult, right? Before, after he's catapulted, and his final velocity, let's say right as he's leaving the catapult, is 100 meters per second. It's a fat cat. Let's say the mass of the cat is 20 kilograms. So then you can ask, what's the impulse? What's the impulse that the catapult puts on the cat? So the change in momentum would be the final momentum minus the initial momentum, right? But the initial momentum is 0. So this is just what? 20 kilograms times the final velocity, which is what? Final velocity is 100 meters per second, right? Which is what? Yeah, 2,000 kilogram meters per second. So kilogram meters per second is the typical unit of momentum.
Does it have a name?
No, not that I know of. I mean, I don't know.
How close to the catapult?
Call it a
We call it the I don't think that would be deserved. I'm not even Dr. Cook here. I'm really Mr. Cook if you think about it, because I only have a master's in physics. So, you know, you can call me doctor in math class. Don't call me doctor either. I mean, they really should find somebody more qualified to teach this course, honestly. Oh, okay, so, where am I? Oh, yeah, 2,000 kilograms. Now, you can ask interesting questions like, what's the average force put on the cat during the catapulting, right? Now, so it depends on how fast it happens, right? If the catapult it acts over a second versus over a half second versus over a tenth of a second, you'll get different average forces, right? So if the time that this happened was, say, 0.1 seconds, suppose there's 0.1 seconds between the time the 1-ton thing drops on the catapult and it hits the ground and the thing goes flying off, right? then if the change of time was 1 second, then the average force, and this is just average, okay, would be the impulse divided by the change of time, which in this case would be 20,000 newtons. Which is probably not going to do good things to the cat. There are some great YouTube videos of cats being catapulted. Some of them not entirely truthful. They're basically based on some similar set of parameters to what I showed you here. Okay, so is momentum conserved? Right? Is the momentum for a particle conserved? I think the question basically boils down to, is there a force that's acting on the particle, and is there enough time for that force to change the momentum? Let me show you an example where there is enough time for it to change the momentum. It's a problem we've already studied. I'm just going to study it now from the perspective of momentum. So let's study momentum of mass SM under projectile motion. This one will be a little bit more interesting. It's genuinely two-dimensional. So here we go. We start with, say, mass M. You've got an initial velocity v naught, right, at some angle. Let's say theta. Right, and then it goes this parabolic motion, right? Like so. Eventually it's over here, right? And we can work it out. What you end up with is, if there's no friction, you end up with the same speed at the end, but instead of angle above the horizon, the angle below the horizon, right? Let's see here. And then there's another interesting time we can think about, which is the zenith of the flight, right? Up here, we can talk about, let's say, v1. Let's contrast the momentum at these different places. Okay, so what's the initial momentum here? Well, we can write a momentum as a vector. It's p naught x, comma p naught y. Let's talk about those separately. So basically, it boils down to what's the let's see here. So the x component would be what? V naught cosine theta. The y component is v naught sine theta, right? So this is actually what? It's m v naught cosine theta, m v naught sine theta. You have both x and y momentum at the start. Right. What's the momentum at 1? At 1, what would the momentum there be? What's the y momentum at the top? 0, right? Yeah. So we have p1x 0, and is there ever an x force? I mean, is there ever a force with a non-trivial x component acting on this mass in this motion?
No.
There's not. Right? So that means that the x momentum is conserved. It's the same at the beginning as it is in the middle as it is at the end. It's always whatever that value is. It's always m v naught cosine theta. And then finally, what's the, let me call this the final df. So the final momentum pf would be what? Pfx, Pfy, which would be m v naught cosine theta, no surprise there, and minus m v naught sine theta. I'm using some things we derived before in terms of how the velocity changes with time, Now, can we see how these results coincide with this thing I just said about what is the force acting on this particle, and how does that force change the momentum?
Oh, that's interesting.
The force is mg. It's mg here, it's mg there, it's mg everywhere. It's always mg. to be more specific, it's really, you know, I mean, the gravity force is what it's actually what? It's minus mg y hat, right? So what happens if I look at the change in momentum, let's say, from time 0 to time 1? Well, I'm telling you it's P1 minus P0, which is what? 0, comma, mv naught sine theta, right? Is that right? Now that should be very good. It should be minus very yes, very good. Because P naught has the non-trivial thing. And so this is supposedly equal to the integral from T1, or in this case, our time 1, we can just take 0 to the time of the top of flight, time 1, of what's the force? Well, the force is minus mg y hat dy, excuse me, dt, right? Okay, is this actually true? What is time 1? What's the time at the top of the flight? Do you guys remember how we figured that out? We have Vy, which is equal to what? V naught sine theta minus GT1, right? That's equal to 0. So you see T1, the time to the zenith of the flight, T1. And I'm assuming that it begins and ends on the flat ground, right? I'm not getting into those annoying side cases where we start with the motion like when you're off the ground or something. I saved that for your test. Let's see here. I mean, I give you guys a note card, so if I give you the standard problem, you're just going to give me the formula back. And I don't know what I'm supposed to do with that. I mean, if this is like a course in collecting formulas, then like, bravo! But like, you're supposed to be analyze stuff, so I can't give you a note card and give you standard problems, like the most standard problem. I have to always twist it a little bit and get a note card. Would you like me to take away the note card and have easier problems?
Yes.
Half a note card, half easier.
It's kind of an empty gesture, because I already think I'm giving you easier problems, so how can I distinguish the hypothetical easy problems I'm going to give you versus the easy problem I'm already giving you?
What if you give us an answer?
You could give us all the answers.
Why are we even here? Let's just like stay home and just give you guys grades.
I like that.
It's like, in fact, why do we have buildings? So it's everything grades, degrees, you know? So time 1 is actually V naught sine theta over G. So that's this time. And so I'm integrating, you know, mg, which is a constant, y hat, dt. So that is actually minus mg t y hat, evaluated from 0 to V naught sine theta over G. And guess what? We get minus mg V naught sine theta over G y hat, which is otherwise known as minus m V naught sine theta y hat, which shockingly is the same as this, right? What do you know? The integral of the net force is in fact equal to the net change of the momentum, the impulse. So I might ask you a question later which is more interesting, something like, here's more interesting, what makes this problem more interesting is, instead of letting the mass stay together, suppose there's an explosion at the top, right?
Fireworks.
And maybe this thing fractures into 2 pieces, right? So, or maybe there was a cat. I don't know, maybe there was a cat. And he was riding the projectile, and then up at the top, like it explodes in the cat, or pieces of the cat. One goes this way, one goes that way. You can ask where they land. You know, if it's a closed system, the momentum is conserved. Well, not quite. The momentum changes in this problem because gravity acts on the system. Is my point. So this is a problem we could work where momentum is not conserved, and yet it changes in a regular way, in such a way we can manage it. You already managed it earlier in the course, like, so, yeah.
So if that happened, it would be the center of mass of the entire system of pieces of cat that would land in that spot.
Right. Yes, yes, and then the other ones would be kind of,
Yeah.
yeah.
Would mass be conserved if we took into account the change in the momentum of the Earth?
Well, as far as mass being conserved or not conserved, I guess strictly speaking, no. When there's an explosion, some of that mass energy, some of the mass is being created, is being converted into energy. And there's other chemical processes that happen and so forth and so on. But to a good approximation, as far as classical mechanics is concerned, mass is conserved, yeah. I mean, we have this slogan, mass is, we have a slogan, energy is neither created nor destroyed, it changes form, right? In other words, it's destroyed to make other forms. All right, this problem is too hard. Let's go back to an easier problem. So, I have started the discussion with something which is actually relatively hard to understand. Let's go back to something easier to understand. One-dimensional collisions. So basically, gravity is negligible because everything we're thinking about is on the level. So just a horizontal flat plane. There could be friction. There might not be friction. Actually, it doesn't really matter because we're talking about collisions which happen over an instant of time. So I have some mass, let's say A, and over here I have some mass B. All right. And so, I have V1A, and I have V1B as my, as just the starting. That's before. And then there's a collision, right? And so that means that they come together, right? Marissa's rethinking your choice of seats right now.
It's going to break by the time this course is over.
And we're all gonna
You keep threatening to destroy them in various ways.
Yeah. So you have a collision, right? And then stuff. And then it either. Well, it doesn't have to bounce, right? It could go like this, right? Or if this one has more, it could go like that. Maybe they could just stick together and just sit there. I suppose is another possibility. There's lots of different possibilities, right? Depending on whether they stick together or bounce off each other, and so forth and so on. That's what we want to understand. What are the possibilities? So I'm just going to set up just sort of a generic mathematical setup. Here's after, all right. I'll still say MA, and and here's B2A. And by the way, guys, I'm just to be less annoying in terms of signs. Let's just always think of this as being positive direction. So here you go, V1B, be positive, it's that way. Of course, to actually have a collision, I would need V1B as negative and V1A is positive or something otherwise. Or I need V1 is fast enough that it catches up with the other one. That's another possibility, so forth and so on. And then, so here's after. I don't know if this picture is maybe not doing it for you yet. Sorry. So before, after. And so before and after. And so what I'm saying is, let me just draw a picture. So the collision, there's this collision, and the delta t is exceedingly small, right? So the change in momentum for the system, which would be the force, net force times delta t approximately, right? As delta t goes to 0, that becomes exact, right? And so if I ask for the velocities just before and just after the collision, even if there's friction involved, the fact that there's so little time for that force, the friction force, to change the momentum of the system, it means that the friction it can be ignored as far as the collision is concerned, all right? So in a collision, momentum should be conserved, okay? So how do you write momentum conservation for this collision? Well, so we have the momentum at time 1 is equal to the momentum at time 2. That's it. I don't need vectors because I'm in one-dimensional case, right? I mean, I don't need vectors here. I could just use right for positive, left for negative. And in view of those conventions, momentum conservation just looks like this. MAV1A plus MBV1B is equal to MAV2A plus MBV2B. And that's all she wrote. That's it. Just have to solve that equation and understand it. So let me give us the problem. Work it out. Try. Any question? Now, of course, if this was a two-dimensional problem, that wouldn't work for us, right? We couldn't just treat it as one equation. You'd have to think of it as a vector equation, and you'd have to conserve not just the x momentum, you'd also have to conserve the y momentum, and you'd have to break it up into components and do all that vector addition stuff that we know and love from before. But one-dimensional start with. So, for example, before, let's say I've got 5 kilograms, and it's going at 10 meters per second that way. And then over here, I've got 6 kilograms, and it's going at 1 meter per second that way. And then suppose that they stick together, right? A and B. So suppose they stick together. What's the final velocity? They stuck together. It's part of the sticking process. Yeah, they smushed. Don't ask me these questions. Okay, so we've got you've got 5 kilograms times 10 meters per second, right? Minus 6 kilograms times 1 meter per second. This is what? This is the initial momentum, right? There's the right momentum is positive, the left momentum is negative, and then that's going to be equal to what? The final momentum, right? So you've got MA plus MB, which is what? 11 kilograms times VF. I hope you can see by now that writing kilograms isn't really necessary, provided you do kilograms everywhere, because in momentum conservation, the units are always going to be like there's a kilogram, there's a kilogram, there's a kilogram. So if I had just written 5 and 6 and 11, I wouldn't have lost anything mathematically, right? Okay, so apparently VF is what?
4 meters per second.
You said 50 minus 60 over 11.
50 minus 6.
50 minus 6 over 11, rather. Yeah, meters per second. Which is what? 54 over 11? 54. Oh, I can't do math. Oh, it is? Ah, cool. Oh my goodness. That is so totally accidental. So yeah, I thought you were being sloppy, like it's 4 meters per second. I'm like, it should be a decimal. What are you talking about? Oh my goodness, I could not make that work out like that if I wanted to.
You need to write that one down so you can.
Yeah, I really should. It should be a test question.
Oh yeah, that's really
Yeah, really.
Kinetic is imaginary.
Okay, so part of the joy of being a physics instructor is telling you the meaning of words and then criticizing you for not knowing the meaning of those words on the test. So one of the principal words that I like to jump all over you for not knowing on the next test is an elastic. Elastic versus inelastic collision. Elastic, these are very precious. These are unusual. In the world of collisions, these are the really special ones. These are like the totally bouncy collisions. Oh, like a billiard ball. If you have a really, really good quality pool table, that you get nearly elastic collisions. All right? And in elastic collisions, kinetic energy before is equal to the kinetic energy after of the system. In elastic collision, you have kinetic energy before is not equal to the kinetic energy after. And usually, unless there's an explosion, we're talking about a loss of kinetic energy in the form of heat, sound, smooshing, whatever. So this example, I just made it up. Is it elastic or is it inelastic? Now the answer, it was sticky, so it's inelastic, would get you partial credit, but to give me full, I mean, if you really want to show me that it's inelastic, you need to show me that the kinetic energy before is not equal to the kinetic energy after, right? By saying that elastic collisions are bouncy and inelastic collisions are sticky, those are slogans, those are not the real McCoy. You shouldn't accept those as actual arguments, those are just descriptions. Mathematically, we have to check. What's the initial kinetic energy?
Would it be the same as saying 11 kilograms times 9 meters per second? Or one half. Can you evaluate the kinetic energy of the whole system at once? Or
No, you have to add
separately?
kinetic energy is additive. You add the kinetic energy for each mass separately. So like I have to do 1/2 times 5 times 10 meters per second, 1/2 times 6 kilograms times 1 meter per second squared. What's that work out to?
Do we add it or subtract because of the?
This is 100 divided by 2 is 50. 50 times 5 is
50.
yeah, 250. So I have 250 joules plus what's this? 3 joules. Man, that's sad. Okay, 3 joules. And so we have a grand total of 253 joules initially. What's the final kinetic energy? Now, at this one, you can just do 1, right? KEF is
So
1.
since the velocity is squared, it doesn't have addition.
1/2 times 1 kilogram. Obviously, 11 kilograms
2 millimeter.
times 4 meters per second squared. Then you add 8 times 11 joules. You get 88 joules. It's close. Not really. So in the process of this collision, you have lost about 60–70% of your kinetic energy.
Where did that go?
Heat, sound, the process of deforming the solids to stick together, other stuff.
Also, a lot of the times it goes straight into the earth, right? Because if you use the earth as the starting point for motion. Does that make any sense?
I mean, it could go into, like heating of the road, frictions, other things like that, yeah. I mean, strictly speaking, the masses aren't entirely a closed system, right? So, yeah, the energy can leak out other ways. And despite Oprah's claims to the contrary, like, they put the energy out there, but it doesn't come back to them. The universe doesn't care. It's not true. It's just gone. Yeah.
It is indifferent.
Sorry, Oprah's not really on anymore. I used to go to a church where the pastor talked a lot about Oprah as kind of like his metric for where society was at in terms of illogical New Age mysticism, which is go-to. I learned lots of little tidbits about Oprah that I would otherwise never know.
Can we just do a quick run through of if they bounce or Kinetic?
Yeah, sure. So suppose let me be just a little bit more greedy. Like suppose that this general one was an elastic collision, right? What would that look like? So that would give you 1/2 ma v1a squared plus 1/2 mb v1b squared is equal to 1/2 mb v 2a squared plus 1/2 m, oh, this was b-a, sorry, mb v 2b squared. So if you have an elastic collision, I get not only momentum conservation, but also kinetic energy conservation. By definition, okay? Yeah, so you can solve problems subject to both of these conditions if you want. Obviously, it's trickier. Yep.
Just for the purposes of convenience, when we like maybe show you this on the test, can we kill the halves?
Of course. I mean, yeah, I'm about to do
Can we
that.
just, okay.
So let's see here. So yeah, equivalent condition would be MA V1A squared plus MB V1B squared is equal to MA V2A squared plus MB V2B squared. And I suppose if you wanted to make this cleaner, you could isolate the MA in terms of V1A squared minus V2A squared, right? And that's equal to MB times V2B squared minus V1B squared, right? I mean, you could do that. And then you got the difference of perfect squares, so you could do some algebra, right? We're allowed to do algebra. Do some algebra. So difference of perfect squares. What happens? What happens? Let's see here. That would give me MA times V1A minus V2A times V1A plus V2A is equal to MB B 2B minus V2A times V2B plus V2A.
Would not be V's on that, right?
It is possible I have made a mistake. Yeah, excuse me, all these over here.
Shouldn't some of those be one B's?
So 1 minus 2. Let's see here. I should have 2 minus 1.
Rotation is the level.
2 minus 1. 2 plus 1. Thank you. Very good. Now, you notice something here. This first equation, you know, we're having so much fun doing this. Maybe this first one we could combine somehow. This is MA times V1A minus V2A is equal to MB times what? V2B minus V1B. So let's see. Seems like that ought to be useful. Can we do anything here? Do I have V1A? I mean, I have MA. Like that's this, right? Right? Same term? So I can trade that for MB times V2B minus V1B. Yup. And then V1A plus V2A equals MB, V2B minus V1B, V2B plus V1B. Hey, that's pretty awesome because now the B's cancel. I mean the masses. They cancel.
What just happened? Yeah, what, could you explain?
Substitution.
How did you
Because
substitute?
now you just have V1A plus
Because I
V2A.
have this pattern here, right? Momentum conservation gives me this relation. I use difference of perfect squares. I'm just identifying that this right here is this right here.
But then the
So I can trade that expression for this right here expression.
But then the V2B minus V1B also cancels.
Indeed.
So then you're just left with the velocities have to be equal.
Not
At-
quite. We
yeah,
have V1A plus V2A is equal to V2B plus V1B. Not quite, that's a mixture, an admixture of things. Let me rewrite that in a way we can use it. Now, this equation is obviously superior to this equation. Why? That is a linear equation. It's just a difference of velocities, right? This is square root of velocities. This is a pain. That's nice. So let's see here. This is actually what? V1A minus V1B is equal to minus V2A minus V2B. And there you go. What that says is that the relative velocity before is equal to minus the relative velocity after. And that, in a nutshell, is the easiest way to characterize elasticity of a one-dimensional collision. Just the difference in velocity before and after is equal but opposite. So with that in mind, I can work an example pretty easy. So like here you go, 10 meters per second, 2 meters per second. That way, here's A, here's B. I can tell you collision is elastic.
So what decides which one?
And VAF, the final velocity for A is equal to, I don't know, 3 meters per second.
Oh, I'm so sorry.
I guess she didn't want to learn physics.
I just people coming to class and like committing to it, you know. Favorite graduate classes when some freshman walked into like a 700, 800 level class at NC State. And they just sat there the whole time, like, they really committed to it.
It's too bad.
I know they don't care about algebraic topology, but I guess they learned something about it. So the relative velocity before dB minus dA would be like, let's see, that'd be minus 2 meters per second, minus 10 meters per second, right? So the relative velocity before, in this example I'm working, minus 12 meters per second. So that says that VF minus VAF is equal to 12 meters per second, okay? But if I tell you that VAF is 3 meters per second, that tells me that VBF minus 3 meters per second is equal to 12 meters per second. So therefore, the velocity of the remaining mass is 15 meters per second. One of the things that's really wacky about all that is I didn't tell you the masses. But once I put masses down there, I have to be more careful because whatever velocity I tell you before and after, I actually have to be able to I have to be able to conserve momentum, but I guess the algebra we just went through means it's going to happen. So anyway, that's a nice, what I'm trying to tell you is this is a super nice trick formula for the elastic one-dimensional case. By the way, this is not true for two-dimensional collisions. It's no longer so simple. Generally speaking, you do have to conserve kinetic energy. That's just what it is. Oh, let me give you your test back. I have not posted the solution yet. So,
So the first one.
Isaiah?